Okay. So 4 things. What do I mean 4 things? Well, if you want to completely describe a gas, to describe everything about it, you need to measure 4 things. Actually, if you measure 3 of them, you can figure out the 4th. But there's 4 things that are interrelated. Okay? Pressure. Talked about that already. Temperature. Because those were the 2 definitions we came up with because of the kinetic theory, right? Pressure is the collisions, temperature is a measure of how fast they're moving. Okay. Volume. How much space you gave them to move in. If you give them more space versus less space. Bigger container, smaller container. And the number of particles. How many pieces are hitting. And we're going to measure the number of particles in moles. Okay, now, do scientists want 4 things to change at the same time in an experiment? Okay. So if you think about the experiment you did, you kept 2 of them constant. Once you sealed that syringe, you didn't let the gas go in or out, so the number of particles stayed the same. And the temperature stayed the same. We didn't heat it or cool it, assuming the same temperature as the room. Right? So we left those 2 constant, so by changing one, we could see how it affected the other. And that's the way they do it. They hold 2 constant and see what happens with the other 2. Okay. So for most of this chapter, we're going to assume gases behave ideally. Ideally means they follow the kinetic theory perfectly. Reason why we do it is because it makes the math easier. Say, well, hey, is there anything else I can use to make the math easier? They do it just because it makes the math easier? No, they don't do it just because they make the math easier. Because it works fairly well. Okay? When we get to the end of the chapter, we start talking about what happens when you don't get to ignore that. You'll see why you don't want to solve those problems. Okay? It works fairly well. Okay? So it assumes the particles have no volume and they don't attract each other. Because kinetic theory, all the math is based on the fact that the molecules can be anywhere in the container. But technically they can't be in the same they can't be where there's another molecule. So technically you should subtract that space out. But because molecules take up such a small percentage of the space, it doesn't affect our math much. And we said that there's no attractive forces between molecules. A couple of reasons why we know that's true. Not true. One, we studied the forces between molecules and found that, hey, some things evaporated faster than others. That there are forces between molecules. Fact is, the other way is, if there weren't attractive forces, we wouldn't have any liquids or solids. Liquids or solids are when they stick to each other. If they never stick to each other, you wouldn't have them. So liquids and solids are proof that this is not true. See, so it's not true. It's an idealized gas. Scientists do this as a fairly common technique. Take the idealized view and then inject the real world into it and see how the real world really affects it. So we need to know when it's okay. When do we trust our ideal gas calculations and when shouldn't we trust them? We know we made some assumptions. We know the assumptions aren't true. When are the assumptions true? When do the assumptions work and when don't they work? Well, they work at high temperature, and at low pressure. What do you mean by low pressure? Right near 1 atmosphere. Get much above 1 atmosphere, things start going a little bit wrong, but we're going to trust it anyway. Yeah?
So then is temperature and volume?
We'll find that out. Okay, well, this is, so high temperature, the reason why high temperature would do it was because if they're moving fast, they're not next to each other very long. If they're not next to each other very long, they can't stick. Does that make sense? If you're not anywhere near each other, you can't stick to each other. So if they're moving fast, they're not next to each other, so they bounce off fairly well. Okay, and but that would give you high pressure because you're moving the molecules fast. Okay, low pressure. Why low pressure? Because the way you get low pressure is you move the molecules far apart. If you move the molecules far apart, they take up a smaller percentage of the space. So the higher the temperature, the lower the pressure, the better we can trust these results. Okay, so Charles' law. Now that pink piece of paper I gave you, oops, stop. Let's not do Charles' law first. That pink piece of paper I gave you was all the examples we're going to do in this chapter, so that you don't have to take the time to copy them down. Does that make sense? Because you see, you spend a lot of time writing this just to get the question down. So I've given you the questions ahead of time so that we can, so you don't have to spend that time copying. I'm trying to save you some time. Save us some time. Okay. So Boyle's law, what you were supposed to discover. Hopefully you discovered this. That at constant temperature, pressure and volume are inversely related. I really should have a comma in there. Oops. What the heck? Where's it going? All I want to do is put in a comma. So that means that as the pressure goes down, the volume goes up. So, shouldn't be a big surprise that in order to make a gas smaller, I have to push on it and squeeze it. Okay? One goes up, the other one goes down. So that's Boyle's law in words. And when they say inverse, they literally mean take and flip it. So twice the volume, half the pressure. 1/8 the volume, 8 times the pressure. Flip it. Here's what that looks like as an equation. P times V equals K. Strange thing, you're figuring out K on your lab, but scientists never bother to figure out K. Why not? No, if it's constant, it's worth figuring out. It's constant for that number of molecules at that temperature. Okay? If you got a different number of molecules, you're going to get a different K. If you've got a different temperature, you get a different K. Okay? So it's constant for that temperature and that number of moles. And are you going to be able to control all those things real well? No. So why bother to write this? Because if I write this, then I can write that. P1 times V1 equals P2 times V2. Or just P1 V1 equals P2 V2. Where P1 is the first pressure. Oh, no. P1 is one pressure. V1 is the volume of that pressure. P2 is a second pressure. V2 is the volume of that second pressure. Why does this work? Well, because P1 times V1's got to equal K, and P2 times V2 has to equal K. So this is K equals K. Okay. Like to do proofs every once in a while. K equals K. So that's how we solve it. And when you solve it, you can use that equation. If I give you 3 of the numbers, you can figure out the 4th. So I can tell you 2 pressures and 1 volume. That means you start off this pressure and this volume. Here's the new pressure. What's the new volume? Or vice versa. 1 pressure, 1 volume. Here's the new volume. What's the new pressure? Graph-wise, should get something that looks like that. Okay. The graph of 1 over V. We got the graph of 1 over V in your extension, which tended to be a straight line, right? Okay, so, hey, question number 1. Hey, question number 1. Balloons filled with 25 liters air at 1 atmosphere pressure. If the pressure's changed to 1.5 atmospheres, what's the new volume? Now, I'm going to go through a process here that you want to get used to because I say, well, it can't be that hard. We only got 1 equation. When we're done, we'll have 9. So you have to pick the right one. Okay? So the way you pick the right one is label what they give you. See what your options are. Okay? So they told me 25 liters, that's a volume. They told me 1 atmosphere, that's a pressure. They told me 1.5 atmospheres, that's a second pressure. So I'm going to put a P1 and a V1, a P2. Now I just have to decide, does that V, the 25 liters, go with 1 atmosphere or with 1.5? When it was 25 liters, what was the pressure? It was 1.0, so that's situation 1. And what is the new volume? They're asking for situation 2. They want the volume when the pressure is 1.5 atmospheres. So think of them as sets of data sets. 1 condition, 2nd condition. Hey, anybody know of an equation that has those pieces in it? Okay, I'm sure it'll boil to the surface. P1 V1 equals P2 V2. Now for the algebra time, what do I want? I want V2 up top by itself. So to get V2 by itself, divide both sides by P2. Pretty simple algebra. So that's what we're going to do. V2 equals P1, 1.0 atmospheres, times V1, 25 liters, divided by 1.5 atmospheres, which was P2. Show your work, include the units. So 25 divided by 1.5 is, with 2 sig figs, 17. And what units? Well, the atmospheres cancel out, so I'm left with just liters. The units should always work out when you do this. If the units don't work out, you did something wrong. Okay? Units will always work out. Extra is super tough. Okay. So let's try another one. Number 2 on your list. Second balloon. 73 liters at 1.3 atmospheres. What's the pressure needed to change the volume to 43 liters? Well, 73 liters was a volume. 1.3 atmospheres was a pressure. What pressure? So they want this second pressure. So the other one must be the first pressure. And does 73 belong with 1.3 or, well, it must belong to 1.3. So that is V1. And 43 liters is V2. Anybody know of an equation with those pieces in it? Okay, that would be P1 V1 equals P2 V2. Now we're solving for P2, so I want to divide both sides by V2. So I need to multiply P1 and V1, 1.3 atmospheres. Times 73 liters divided by 43 liters. 1.3 times 73 divided by 43 is 2.2. The liters cancel out, and I'm left with atmospheres. Do I have to work in liters? No, what has to be true is the volumes have to have the same unit. Do I have to work in atmospheres? No, the pressure can have any of the pressure units as long as they're both the same. If they're not both the same, change one. So that's how you do Boyle's Law problems. Extra super tough. It's different than what we've been doing because we haven't used formulas for a while, right? So this is different than stoichiometry. We figured out our own equations along the way. Here they give them to us. I think that's a little easier. Okay, so next, now we'll do Charles' law. So Chuck's law, no, Charles' law. I don't know him that well. Okay. Charles' law deals with the relationship between volume and temperature. It says the volume of a gas is directly proportional to the Kelvin temperature if the pressure is held constant. So let's see if we can use the kinetic theory. It's for me. I left this number. Don't care who it is, just push off. I always want to answer it. Hi, this is Mr. Green. So let's try to explain this. Okay, this one's a little bit tougher to explain. Pressure and volume is pretty easy. If you make the containers smaller, they got to hit those container walls more often. If I make, does that seem reasonable? That's why pressure and volume are inversely related. The smaller container, the more collisions I'm going to have. Okay, volume and temperature is a little harder. And the key part of it is that you have to keep the pressure constant. So if I heat up a gas, what's going to happen to the particles? They're going to move faster. So they're going to hit the walls harder, which would increase the pressure, which I don't want to happen. I don't want the pressure. I need the pressure to stay constant. So the only way the pressure can stay constant is if I move the walls out of the way. Right? The walls if I make a bigger container, then I can push then they're not going to hit as often, even though they're moving faster. So I can cancel out the effect of them moving faster. So the key is I got to keep the collisions the same. So when they're moving faster, the container has to be bigger, so they have to travel further before they hit the wall. See reasonably? So it's got to be a bigger volume if I want to keep the same pressure. So the secret is that I need the pressure to be constant. Okay? Directly related, what does that mean? As one goes up, the other goes up, so twice the temperature, twice the volume. Here's what it looks like as an equation. V equals KT. Where K is some constant. Once again, nobody bothers to figure out this constant. Okay? Because you'd have to keep the pressure and the number of molecules the same for everything. That's the only time it's true. So nobody bothers to figure it out. But if they did, they'd write it this way. Everybody see that's what they'd write? Just divide both sides by t. So the way it's useful is this way. V1 over T1 equals V2 over T2. Key component, this only works if you're in Kelvin. So if they give you the temperature in Kelvin, or give you the temperature in Celsius, change it to Kelvin, do all the math in Kelvin, and if they ask for the answer in Celsius, change it back. Okay? You can't do, the math in Celsius doesn't work. And here, let me show you an example of why it doesn't work. Okay? So, if I'm at negative 10 degrees Celsius, and I double the temperature, what temperature is it now? See, doubling the temperature in Celsius can lead to decreases in temperature, right? It's because it's got those negative numbers, right? Everybody see that? So you got to change it to Kelvin, or it won't work. Okay, because Kelvin's really about measure. The bigger the Kelvin, the faster they're moving. Okay? It's true of Celsius, but negative 10 to 0. What have I done to the temperature? I've added, but that's not going to work for this equation, is it? Okay. So this is going to be the graph of a straight line. So when you graph volume and temperature, you get a straight line. And Charles found that. They got a straight line. Okay? And he tried it with one gas, and things don't stay a gas forever, so below a certain temperature, he just extended the line. So he took data up at these points. He took data here and here and here and here and drew this little blue line, and then he extended it back here. Okay? And he did it with a different gas. And when he did it with a different gas, he drew his line drew here, here, and here, and here, and he extended it and went right there. That's why it's dotted. He couldn't measure that because it's not a gas at that temperature. Things turn into a liquid, you get them cold enough. Right? And he took another one. And he extended the line. He graphed it, and he extended the line. And what he found was when he extended the line, all of them pointed at the same point. They all pointed to a temperature, that's a temperature, right? Where the volume is 0. And that temperature was right about negative 273 degrees Celsius. So the first definition of absolute zero, had nothing to do with the kinetic theory. First, they found absolute zero, said, hey, that must be a lowest temperature. There must be something special about that temperature, because all lines point to it. The temperature where all the gases would have 0 volume is the same for all gases. And no matter how much you start with. Okay. No matter where you start, they all point to the same spot. And that's the temperature where they have no volume. That was the first definition of absolute zero. Because this was done before they knew there were atoms. Remember, atoms didn't show up till late 1700s. Boyle's did his in the early 1600s. Charles, late 1600s. So they did all this but have no idea why it worked. So they knew there was something special about that temperature. They didn't know why, but they knew that all lines led to it. Okay? So that was the first place they got the idea that the lowest temperature of some way. So, question number 3. Question number 3 is the one that's going to be missed most often when when I give you tests. Nah, it's algebra. It's the algebra that messes you up. Okay, so 2.5 liters. 2.5 liters is a volume. 25 degrees Celsius is a temperature. 4.1 liters is a second volume, so that other one must be my first. Which did the 25 degrees belong to? 2.5 liters or 4.1 liters? 2.5. So it belongs to 2.5, so it's a 1. And it says, what is the temperature? So they're looking for temperature 2. So looking for the temperature when it's 4.1 liters. Okay. V1 over T1 equals V2 over T2. And here's where people make the mistake. Okay? I'm going to make the mistake lots of people do. Divide both sides by V2, and you get T2 equals V1 over V2 times T1. Is that math right? Nah, because it's not T2, it's 1 over T2. Right? So I don't want 1 over T2. So you've heard me say it a few times, but I'm going to repeat it. Get the thing you want on top by itself, and do it in that order. Get it on top first. Okay, there are bunches of ways to do this. Let's talk about bunches of them, and then I'll try to teach you a different one that's a different way of thinking about it. Okay, I can cross multiply. So I can do cross multiply and get V1 T2 equals V2 T1, and then divide both sides by V1. That works, doesn't it? Or I can multiply both sides by T2. If I just multiply both sides by T2, those cancel out, and I get T2 V1 over T1 equals V2. Now multiply both sides by T1 and divide both sides by V1. And I get T2. I get the same equation. Okay. Or I can start off and just flip both sides. T1 over V1 equals T2 over V2. I got it up top. Now I just need to get it alone. Multiply both sides by V2, and we get the same equation. All those ways work. I don't use any of them. Okay? I use a simple math rule I learned. If it's on top of one side of the equation, it's on the bottom of the other. It's on top of one side of the equation, it's on the bottom of the other. So when I see this, I say, oh, I need to move these pieces around. I need T2 to be on top. Which side would T2 be if it was on top? It'd be on the left side, so I'll move T2 over there. I'm going to leave V2 where it was at. I want T2 by itself, so I want everything on the left-hand side to go away. So I'm going to have to move V1 to the bottom and T1 to the top. Okay? All four of those ways got us the same answer. I don't care which one you do. But I need to see this equation solved. Okay? Most common mistake is solving it upside down. Okay? And you will know that you did it wrong because you will get a decimal point for an answer, something less than 1. So if you get something less than 1 for an answer as a temperature, that means you're less than 1 degree above absolute zero. Can you expect gas laws to work at 1 degree above absolute zero? Why not? Because they're the gas laws. They're not gases at 1 degree above absolute zero. everything's going to be a solid at 1 degree above absolute zero, so you can't expect gas laws to work if they're not gases. So if you do it upside down, you'll get a decimal point Kelvin, and then you'll try to subtract 273 from it. Okay, but now that we got the right equation, we can solve this thing. So that is, we said T2 equals V2 T1 over V1. V2 was 4.1 liters. V1 was 2.5 liters. And T1 was 25 degrees Celsius plus 273 is 298 Kelvin. So 4.1 liters times 298 Kelvin divided by 2.5 equals 490. 2 sig figs in the 4.1, the 2.5, and the 298. And my liters cancel out, so the only unit I'm left with is Kelvin. If they asked for it in Celsius, I'd still subtract 273. I do all that, subtract the 273, and get 220 degrees Celsius. See, but Mr. Green, my calculator says 217. That's not a sig fig. So I got to cut it off here. And so that was the hard version, because you got to remember to get T2 on top first. If you make a mistake, you'll get a decimal point for an answer, not 220 degrees Celsius, where it would be a gas. Okay, so if you get a number less than 1 Kelvin, you did it backwards. So what's the final volume of a gas? It starts at 8.3 liters and 17 degrees Celsius and is heated to 96 degrees Celsius. So it gave me 8.3 liters, that's a volume. 17 degrees Celsius, that's a temperature. Heated to 96 degrees Celsius, that's a second temperature. Notice I don't put the second T because eventually we're going to get to equations where there's only one temperature. There's only one volume. So that's why I don't put numbers in until I find the second one. Okay. And they want the final volume, so they want V2. So, hey, anybody know an equation with those 4 pieces in it? So V1 over T1 equals V2 over T2. I want T2 by itself, or V2 by itself, so I just have to move that T2 to the other side, or multiply both sides by T2. So I end up with T2, T2, 96 degrees Celsius plus 273 is 369 Kelvin. And 17 degrees Celsius plus 273 is 2.90 times 10 to the second. Why the heck did he write that? Because 290 is only 2 sig figs. The ones place is supposed to count. Right? The one place is supposed to count. So I need that 290 with 3 sig figs. You can write that as 290 point, or you can write it the other way, 2.90 times 10 to the second. And V1 was 8.3 liters. So 369 divided by 290 times 8.3 is, with 2 sig figs, 11, I forgot my Kelvin down here, so I couldn't cancel it out, liters. Okay, and we need to talk about temperature a little bit more, and temperature and sig figs along the way. Okay? But we'll do that in a second. But notice here, does it work in Celsius? Okay, we said directly related. The temperature, 17 to 96, that's more than 5 times as much. Everybody okay where I got 5 times there? Do I get 5 times the volume? No, I don't. 11.11 is not 5 times 8.3. It doesn't work in Celsius. You can't just use the Celsius numbers, you got to change them. Okay, temperature. Okay. So here's what I'm talking about. Your book is going to be guilty of this. They drop their own rules. Okay, so if the book gives you 300 Kelvin as a temperature, you're tempted to say 1 sig fig. Okay. Okay, so that means if that's got 1 sig fig, that means they measured this on a thermometer. It said 0, and they had to estimate that was a 3. So the thermometer went from 0 to 1,000. That was the first line. And 300's about there. Oh, probably further down. Right? That's what 300 Kelvin with 1 sig fig means. Right? Is that what 300 Kelvin with 1 sig fig means? Do you think that they make a thermometer where the lines are 1,000 degrees apart? Would you buy a thermometer where the lines are 1,000 degrees apart? Okay? So, if they give you a temperature, assume it's good to at least the ones place. Because the worst thermometers I've seen are backyard thermometers that go every 10 degrees. Nobody buys any thermometers worse than that. So we're going to call it the reasonable rule for temperature. Let's be reasonable. Nobody would buy a thermometer that's that lousy, so it's not reasonable to say that that's got 1 sig fig. Lava, for lava, Kelvin and Celsius are about the same. They're only 273 degrees apart. Lava's at about 2,500. Yeah. And Kelvin. Sun's 1,000,000. There's no upper limit to temperature. There's a bottom, there's no top. You want them to go faster, just keep heating them. Okay? There's a bottom, but there's no top. Does that make sense? Okay. So that's actually where I want to stop today. So give you a little preview of where you're going next.